But what I'm going to talk about today is solar geoengineering. I was saying to David earlier, I refer to it as a bad idea whose time may nonetheless come. And I think all of that's right. Um, uh, but I want to explain why I think this very controversial field is one that requires, or merits anyway, additional research, and where I think this may unfold. But to start in with a couple of introductory thoughts, we have breached the 1.5C target that was the minimum target, or the stretch goal, maybe I'll call it, for the Paris Agreement. It's not clear that we've passed it permanently with the El Nino, La Nina, rather, part of the Southern Oscillation. We're now in a slightly cooling phase. Whether we will cool below 1.5C remains to be seen. Moreover, this isn't the way the IPCC defines these targets. We're meant to average over a 20-year period before we will declare that we're over 1.5C. So we're sort of over it, we're sort of not. We're probably in a zone where we will pass and unpass 1.5C repeatedly over the next several years. But we're here much faster than people thought we would be, because the concentrations of CO2 in the atmosphere continue to increase. This is the Keeling curve. I think of it as the most famous curve in climate studies, but it's the measurements from Mount Mauna Loa in Hawaii of the clear air CO2 levels since 1957 or so. And you see it's going up and to the right. I can't discern any plateau there yet. We're just continuing to fill the bathtub, and I am pretty confident that we will continue to fill the bathtub. But that's concentrations, not emissions. The Paris Agreement, of course, hoped to limit climate change to no more than 2 degrees C, with efforts to maintain it at 1.5. Again, we've sort of hit the 1.5 already. I'm pretty confident we will hit 2C before 2050. That's a personal guess, but I'd bet a fair amount of money on that. I'm afraid it's going to continue to get warmer. When the Paris Agreement was agreed, there was an outcry. The intent coming into Paris had been the 2C goal. But the High Ambition Coalition and Alliance of Small Island States said, no, 2C is too hot for us. We want to limit it to 1.5. So the agreement ended up with this rather confusing 2 targets of 1.5 or 2C. But as soon as the diplomats published 1.5, much of the science community said, wait, we never said we could hold climate to 1.5. Where did that come from? And so in 2018, then, the agreement was to Paris Agreement 2015, the IPCC came out with this curve that illustrated the emissions cuts that would be required in order to meet the 1.5C goal. This is a combination of 92 or so computer runs with different models. They've highlighted 4 representative emissions pathways here. All of them have the approximate configuration that in 2020, this was 2018, so 2020 was then in the future, the idea was we may get on a luge run downhill with emissions and plunge our emissions until mid-century, after which time we would have negative emissions. And you might ask yourself how we might have negative emissions. We'll get to it, but we ain't gonna do that. These negative emissions late in the century were necessary so that we would overshoot 1.5 and return to it by 2100 by sucking a great deal of CO2 out of the atmosphere. So that's what you have to believe if you believe that we're going to stick to 1.5. We are, of course, already 5 years past 2020. We know we didn't commence a luge run in respect of our emissions. Our emissions are, in fact, still growing. So this is quarterly emissions, seasonally adjusted since 2010. Broadly, the trend is up and to the right with variation. The big variation is COVID, but it's amazing how quickly emissions recovered from the COVID swoon. And since then, they've continued up and to the right. Now, we've had 2 quarters here, and this is the data is behind by a couple of quarters, but we had 2 quarters below this peak. People wonder if maybe emissions have plateaued, but this is too little data to tell. To me, this probably is still up and to the right. And this is the part where you say, well, wait a minute, Wake, you dummy. Don't you know about the growth of solar and wind power? And yes, I do. And stop calling me a dummy. So this is solar power capacity since 2005, when it was approximately nothing. It is booming. It has is booming here in Australia, particularly, among other places. But Australia is a leader under the current government in announcing and preparing for a huge build out in solar. Renewables more broadly have doubled since 2012, so it's wind as well as solar, although hydropower remains the primary renewable power source by a long measure. So one can be optimistic looking at these curves until you look at this curve. Fossil fuel demand is still growing as well. So we need solar and wind not merely to grow quickly, but to grow so quickly that they begin to cannibalize the energy share of fossil fuels. And that ain't happening. This is our fuel stack altogether. This is traditional biomass. It's never changed. We haven't replaced it. In fact, the amazing thing to me about this chart is that nothing is replaced. Everything is additive. So each time we find a new energy source, it adds on top of the old ones, but it doesn't cannibalize the old ones. So here's solar up here. This is wind. Together, they're 6%. Fossil fuels are 75%-ish, 76% with this math. They were that the year I was born. We haven't made any progress in terms of the share of our energy that derives from fossil fuels. And again, the pie is still growing for renewables, but also for fossil fuels. Such that per the IEA projection, which this is, and one can imagine the IEA has reasons to spin this, so take this with however many grains of salt you wish, but the IEA does not project that fossil fuels are going away anytime soon. This shows a plateau and the beginning of a reduction, primarily due to a reduction in coal. But fossil fuels are going to be with us for quite a while. Because while Australia, Europe in particular, the US, Japan, South Korea, other highly developed countries are reducing their emissions, the vast majority of the emissions today come from the developing world, at least if one includes China in that latter category. And so China's growth, Indonesia's growth, India's growth are overwhelming the reductions that are happening in the most developed part of the world, such that emissions are still rising. And so we are far off track. This is what here's our luge run again, the way we would need to plunge our emissions in order to reach the Paris, I think this is the 1.5C goal. Whereas our announced policies are taking us to, again, what looks like approximately a plateau. So maybe they don't keep growing forever, but it's not clear that they are shrinking our emissions, this is, anytime soon. The scariest thing I'll show you today, which many of you have already seen, is this chart from the AR6. This is the 5 emissions pathways that the IPCC illustrated in the latest AR6 a couple of years ago. None of these are probability weighted. They're not telling you that we've got a 20% chance of this and a 30% chance of that. They're just 5 representative scenarios. But the one that they call the middle of the road scenario, the SSP2 4.5, confusing language that they've thankfully gotten rid of. But this is the quote, middle of the road emissions trajectory. And while you'll note that, so this is 2025-ish, this would reinforce the idea of a plateau that maybe we've reached, and then a slow decline. But this is 2100 and it's not yet to zero. If this turns out to be the emissions trajectory that we take, which may or may not be, it's not a prediction, it's a scenario, this would suggest we don't reach net zero in the lifetime of anybody in this room. It's a next century thing. And if that's true, again, we've got a lot more warming than many of us are expecting, I think. Most important thing in my undergraduate class on climate is this stupid little bathtub diagram. But the point is that even when we get to net zero, we haven't solved the climate problem, because the climate problem is a stock and flow problem. We've got a faucet, that's our ongoing emissions. We've got a bathtub, that's the concentrations of CO2 up in the atmosphere and other greenhouse gases. And we've got a drain. The faucet, our ongoing emissions, is currently running at about 50 gigatons, but let's just call it 50 units and not get confused about the units. 50 in. The bathtub is receiving all of the emissions that we put there. The drain, the natural drain, runs at less than 1 per year. How quickly Mother Nature removes CO2 from the atmosphere. The drain for human purposes is for all essentially clogged. And so if we've got 50 in and we'll call it 1 out, the bathtub, the level of water in the bathtub is going up by 49 a year. So if we did an amazing thing and cut emissions in half from 50 to 25, what's happening to the water level in the bathtub? It's still going up. That's why we've got to get all the way to zero, which is a Herculean task. But if we do, someday I imagine we will get all the way to zero. If we do that, climate damages, or rather temperatures, simply stop increasing at that point, but they don't start decreasing, not for quite a while. And if it's temperatures that inform climate damages, then climate damages after net zero simply plateau. But for the century after net zero, they're much worse than they were in the century before net zero. So net zero is absolutely essential. There's no way through this path that doesn't involve getting to net zero as quickly as we can, but it won't save us from climate damages. We've still got a lot of damages that we're going to have to figure out how to deal with. First stop for questions. Any questions about that?
Do people usually leave at this point, deeply depressed and saying, oh God?
I don't think climate change is going to kill us. We're not just going to stand on the beach while the hurricane washes over. That's not the way this is going to work. We do have a lot of climate change in our future, I'm afraid. But should we hide under a rock and not have children? No, humanity is going to have to find a way through this, but it's not going to be that we have no climate change. That's not going to be the way we're going to solve this, in my polemic view. These are debatable, everything, these are debatable conclusions anyway. But So despite the fact that I'm afraid we've got much more climate change in our future than we're prepared for, I don't think it's the end of civilization or humanity or democracy, or it's going to be a big problem we're going to need to find ways to address. Other questions on basic climate 101? Sir.
Okay. Are there advantages to not achieving net zero easily or quickly?
The reason we won't do it is because it would make us poorer, and none of us want to be poorer. So when climate scolds, and sometimes I'm one of them, say we have to get to net zero quickly, we're not admitting to people that there's a cost to that. And as soon as you note, it's the William Nordhaus of Yale University, sort of framing that there's a cost and a benefit to rapid mitigation, and we've got to find the right balance of cost and benefit. As soon as you realize rapid mitigation also has a cost, then people say, well, wait a minute, maybe I don't want to mitigate quite so quickly. So the advantage is our economy is growing faster today because we are not mitigating as quickly as this would suggest we ought to. And that's a debatable but rational choice. You could imagine if you were God, you might prefer that to a faster mitigation path that makes people poorer today. You might not, but it's not crazy to weigh the cost of mitigation against the pace of mitigation. In all events, voters all over the world are currently deciding, no, I don't want very rapid mitigation. This isn't, people talk about this state of affairs as one that Exxon is doing to us against our will. As I was saying to David, I'm afraid this is a cake we're all eating. I just flew to Australia. Nobody made me. It's our revealed preferences of the choices we're making, in my view. So let me move on, but we'll have time at the end for other questions. So with all that bad news background, I'm afraid we're going to need a wider tool set than simply mitigation, or even than simply mitigation and adaptation. But I'll say one more time, I'm not trying to argue against mitigation. We should do as much mitigation as we can convince each other to do. But I'm afraid that alone won't be the answer, nor will adaptation. We can buy more air conditioners and put a seawall at the mouth of the harbor here to protect against sea level rise. But I think we're going to need more than mitigation and adaptation. The course I teach and the book I wrote focus equally on the following two things: carbon dioxide removal and solar radiation management. But I'm going to touch mostly on the latter here, which is where all of my research lies. This is the napkin diagram, that may be the most famous figure in geoengineering studies, that suggests that if we just burned all the fossil fuel we could ever find, that's the business as usual emissions trajectory. I don't think that was ever a realistic trajectory. The question is simply when we begin to diverge from that. If we cut emissions aggressively, and I'm sorry, this is climate impacts, not temperature. If we cut emissions aggressively, we can stop the increase of those climate impacts. But per the earlier curve I showed, we don't get rid of them. We just plateau them with emissions cuts alone. With carbon dioxide removal, we might actually reduce climate impacts by widening the drain in our bathtub and taking carbon back out of the bathtub much more quickly. But that would still leave this hump, and this hump may be a century or two long when we've got some very unlucky people who are going to live in a hot world. Solar Geo, what it could do is relieve the suffering for those people in that century or two. So carbon capture briefly, not trees. That ain't gonna work. They're too low capacity. Everyone loves trees. I love them. I hug them all the time, but they're too low capacity. They are very fragile stores of carbon. After all, the natural fate of forests is flame. That's what they do. And so they return the carbon back to the atmosphere. That's as well, the amount of carbon capture via trees required to meet that SR 1.5 curve that was produced in 2018. The estimate was that you would require twice the land of India to be newly planted forests, not preserve existing forests, 2 Indias or 80% of Australia. We've got to plant as new forest and water it. That's just not a land use solution that's realistic. We should start with flues. There are still 10,000 or so big smokestacks in the world that look like that, almost all of which are belching greenhouse gases. We're capturing less than 1% of that today. The leading organization that focuses on carbon capture is here in Australia, in Melbourne. But if we want to fish for carbon, the place to fish is where the fish are, and the carbon is super dense in a smokestack. So the way to get going on carbon capture is to start capping flues. But again, there's no economic interest in doing that. And so all of the projects that exist today are experimental in some way. There's no country that has mandated flue gas capture as a climate measure, but hopefully someday we either knock over or put carbon scrubbers on all the flues in the world, and we've run out of flues. Then it's time to capture from direct air. But direct air capture is eye-wateringly expensive. It would cost approximately the size to suck carbon out of the air at the rate that we're now putting it in the air would require an expenditure as big as the entire fossil fuel industry combined. All the coal, all the gas, all the oil together, an industry of that size would be required to capture it at that same pace. So it's very expensive. And so the world in the future will have very difficult questions about who's going to pay for that. Once we capture it, we've got to store it back in the Earth's crust. That's where it came from. And we can't put it in biological stores. It will, or in the ocean, it will return to the atmosphere if we put it there. We've got to put it back down in the crust of the Earth where we got it from. So 2 uses for carbon capture. One of them is the one illustrated in that SR 1.5 report curve, which is to hasten the arrival at net zero. We could still be emitting some if we're capturing an equal amount. But carbon capture is also going to be the way we repair the climate after net zero. And I'm afraid, again, we've got a lot of that in our future over centuries. Switching, though, to solar geo, it is not plan B for problem A. It will not solve the climate problem. It doesn't, it's morphine, not penicillin. It doesn't pull the carbon out of the sky. But it might be how the next century or two survive the high climate impacts that we are exporting to them. So again, it's not an alternative. It's a harm reduction strategy. So there are several solar geo ideas that you hear about, most of which are dumb. People talk about putting space shields at the Lagrangian 1 point between the Earth and the Sun. That might happen, but not in this century. People talk about thinning cirrus clouds. We don't really know how to do that or what sign impact that would have. White roofs is a solution for the urban heat island impact, but it's not a planetary scale solution. Surface brightening by making crops more reflective is GMOs gone wild. I don't imagine that's a likely solution. Or putting tarpaulins all over Arizona. Nobody's going to go for that from a land use perspective. My joke is that there's 1.1 tools in the SRM toolbox. Marine cloud brightening is the 0.1. I'm not sure it's a thing, but there are a lot of smart people who work on it, and so I'm not sure that it's not a thing. Many of those smart people are here in Australia. The leading MCB experiment in the world is the outdoor experiment over the Great Barrier Reef, led by folks at Southern Cross University. They're 4 years into their program. They've done a brilliant job at community relations so that people aren't protesting saying, shut down this experiment. Where are they? The engineering seems to work. They seem to be able to get salt particles into low marine boundary clouds that make the clouds brighter. That's good. It's not clear what the net impact on those clouds is, though. It may be that they're brighter, but they rain sooner, in which case it's self-defeating, but it may not be. It's not clear yet. It's not at all clear that even if we can get the clouds to provide more shade, that it saves the Great Barrier Reef. But it's with the reef, we've got a victim that we want to save. And so this experiment has made traction where others haven't. There was a University of Washington experiment in San Francisco Bay last year that didn't have community support and was immediately shut down. So MCB maybe, but we're going to cool the reef aside, we're going to cool an ocean to try to cool the landmass adjacent to it. That's a pretty indirect way to go about things. There are only some land masses that are adjacent to oceans in ways that where this would work. This doesn't strike me as a planet scale solution. So my focus is stratospheric aerosol injection. Mimicking volcanoes, which the very biggest of volcanic eruptions are known to cool the Earth for a year or two, and we would try to do a similar thing in a man-made way. The key of this chart is the horizontal line in the middle. In order to make SAI work, we've got to be above the troposphere, above the tropopause boundary, and into the stratosphere. I guess that's it. I thought there was another slide. So why do we have to get so high? And if I'm talking off of a slide that comes up in 5 slides, forgive me. I said we've got to be above that line. Why is that? The reason is that if we put the gunk, the aerosol, in the troposphere, it comes back down in a day or a week. If we get it up into the stratosphere, it lasts for a year or two. And so we get roughly 100 times the radiative benefit if we put the stuff in the stratosphere versus if we put it in the troposphere. So we've got to get it into the stratosphere. If we do get it into the stratosphere, in the tropics, then the Brewer-Dobson circulation takes over and takes our injected material from the tropics to the poles. So we could veil the entire planet from just the tropics. And the planet spins, of course, so the east-west distribution is very rapid. So from just a couple of deployment bases in the tropics, you could put an approximately sort of homogeneous veil over the entire planet. Existing aircraft can't get high enough to get into the stratosphere in the tropics. The tropopause, the boundary between the two, is higher in the tropics than it is near the poles. And if we want to veil the whole Earth from the tropics, we've got to get very high. Existing aircraft, passenger jets, military tankers, fighter jets can't get that high. The Global Hawk drone can get that high, but it doesn't carry much. It even left its pilot on the ground. And we need a big leaping aerial dump truck. So none of these planes will do. Nor will alternative platforms, balloons, rockets, cannons, tethered hoses held up by balloons. None of this infrastructure works to get a large mass of gunk to a high altitude, but can do. With a group of retired Boeing engineers, I've designed a plane that could It's not really a plane we would build for various reasons, but as a proof of concept, it demonstrates that we could build a plane that could carry 15 tons of material to 20 kilometers or 66,000 feet, which is high enough to be well into the stratosphere in the tropics. And this could be built with entirely existing engines, wing planforms, control systems. So there's no unobtainium required to build this plane. We could do that. And if we had that plane, then we could deploy our tropical, I've called it, veil from bases at 30 north, 15 north, 15 south, and 30 south. You'll see that those could potentially be in Australia. You would want to spread the bases around the world in order to have redundancy and resilience against natural disasters or changes in political regimes in various countries. But from an array of bases such as that, you could put that veil over the planet. So when might we do this? Not soon. If we made a decision to launch in 2030, which we won't, it would take 10 years to build the first one of those new planes that I just showed you, and another 10 years to build the fleet of several hundred of them that would be required. So geoengineering is often talked about as an emergency intervention. Break glass in case of emergency. That ain't how it would work. This is something we would need to plan for well in advance in order to be prepared if we needed it. Another feature, I'm not exactly selling it on this basis, but it is true that each of mitigation, adaptation, carbon capture, they would all cost in the trillions of dollars per year. Solar geo, we could do for tens of billions of dollars a year. It's 100 times cheaper. Now, it doesn't do the same thing, so it's not a substitute. But one of the facets about solar geo to note is that relative to any other thing we could do, it is cheap, cheap, cheap. Who could do it? I published a paper a couple of years ago. My quickie answer is the US and China have to be the core of any coalition, either or both of them, that could do this. The technological complexity, despite the fact that it's cheap, it's not nothing. You need engines that only a few countries make. And so this isn't something that a terrorist group or Bill Gates or a coalition of small countries could do. This is the domain of alliances of large states. Final thing here in this section, one more section to go. The first question I expect policy makers to ask me about this is, can I do it for my country? The answer is no, it doesn't work that way physically. You put the stuff up in the stratosphere, it advects out of your little country box in a day or two, spins around the world. This is an inherently transboundary and therefore inherently global project. Questions?
Maybe you'll get to it, but what's the stuff that you're putting into the stratosphere?
We start with the devil we know, which is SO2, which after 3 or 4 weeks in the atmosphere would sulfur dioxide, which would evolve to sulfuric acid, H2SO4. We use that as the proxy because that's Mother Nature's gunk. That's what volcanoes blast out. And so it is native to the stratosphere. We've observed what happens when Mount Pinatubo popped off in 1991. Frogs didn't have 2 heads thereafter. There weren't surprising devils that we don't know that derived from it. But it's probably a really bad answer. It's toxic. It kills people, who breathe it. It's the cause of acid rain. And so by the time we actually did this, my guess is we would find a different particle. Why don't we just start with that? The problem remains that it's a devil we don't know. And so if we put calcium carbonate, chalk, or aluminum oxide, or titanium oxide, or industrial diamonds into the atmosphere, we don't know what bad effects it would have. SO2, we know the bad side effects. So, it's one of many poorly researched answers. But if we had to do it tomorrow, we'd start with SO2 and hope to find aerosol 2 soon.
Curious about my understanding is we're aiming for a couple of watts per meter squared you're trying to bring down.
Yep.
A couple of watts per meter squared out of 1300 or whatever the solar constant is seems modest. I was intrigued why you sort of ruled out something in space, like the satellite mirrors in space, or
it would be a much better idea. I just don't think we have the technology to do that in my lifetime. Whereas this, we could do in my lifetime.
Isn't it like putting satellites up, but just like a coordinated system of...
Well, it's much bigger than that and much farther from Earth than that. And we've got to maintain it. So the idea is we would mine minerals from the moon or from Mars and deploy them at this Lagrangian 1 point. It's hard to manipulate.
Why can't it be closer to the Earth, like in satellite orbit?
The amount of satellites, the benefit of L1 is a small system could have a large shadow. With satellites, you would need I never tried to do that math, but it would, I don't imagine you could deflect as much as you would need to with satellites. You know, the Earth's albedo, the reflectivity of the Earth, is about 30%. We just need to get it up to 31%, and it would offset the warming that we're now doing. I'll get to, I think, targets shortly on this. There are different warming or cooling rather targets that one might have in mind, but the amount of material that we're talking about to offset 1 degree Celsius is about 10 million tons of sulfur dioxide, which is a lot, but not that's my $20 billion a year that I referred to earlier. For $20 billion a year, we could be hauling 10 million tons of sulfur dioxide into the stratosphere, and that would cool the planet by a degree.
Sounds a really futuristic, probably hard to believe project. To me, it's just taking into account the possibility of altering the atmosphere is frightening, as is something that we are all linked with. And
something that we are
all linked to the atmosphere, to the
Yep.
quality of
Yep.
the atmosphere. So the first question I would ask is, how quickly can you remove that if something goes wrong?
Firstly, you're understanding the problem correctly. It's a scary thing to mess with the atmosphere. It's the only atmosphere we have. If we mess it up, it's a big problem.
You mentioned, I've been teaching sustainable environment.
Mhm.
I'm very familiar with all the topics you discussed.
Mhm.
And you mentioned quickly about the volcanic eruptions, and there have been some in history that have even been part of paintings. The one where the river in France was freezing. You might be familiar with that. So there might be some cases in which the climate would be completely messed up and would bring some major issues, and this might bring some legal complaints. So who's responsible for this? That would be like a huge damage in another country. So I totally see the point, but like it's a big risk.
So I agree with everything you're saying. This makes no sense unless we are experiencing deadly heat. But if we are experiencing deadly heat, might this be a risk worth taking? I don't know, but the answer is not clear to me that the answer is no. If terrifying heat waves of the sort that the allusion that I made here with this last slide is to the novel, The Ministry of the Future. And I'm not mentioning that here, but there is such a novel, 3 or 4 years old. The plot begins with a heat wave in northern India, which kills 20 million people. And India's response is geoengineering. The way they do it is completely technologically not sensible. But the whole scientific community in my little geo clique was struck by this idea of a heat wave in northern India. Doesn't have to kill 20 million people. If it kills 1 million people, that would be, you know, the Prime Minister of India would just say, this can never happen again. Do something. And in a world where we're having those kinds of climate impacts, the question is going to be, is the risk of solar geo, with all the problems you've mentioned, greater or less than the risk of climate change without solar geo? And that's the risk framing. It's only in that risk framing that this could ever make sense. If things are totally fine, you would never do this. You would never take this risk. I'm going to go with one more, and then I'm going to present a few more.
Do we have the science, or will we have the science at some point in the next 20 years to properly assess whether the unintended consequences of this intervention are quite risky or not? How much do I?
Not only do we not have it, I doubt we will have it by the time we would start the attribution science. So we start this. We started at a small level and we ramp up. India then has the heat wave that kills just 1 million people, not 20 million. India will say that's clearly the impact of the solar geoengineering, and the solar geoengineering coalition owes us compensation for those 1 million lives. And there will be no way for a decade or two to make that attribution connection. It's much more likely due to the underlying climate change, or it could be due to just natural variability, like your rain patterns here in Perth, as I understand it, have changed dramatically 50 years ago. Why is that? Hard to attribute. So the attribution science would be very problematical, which would make the politics of this very problematical.
I'm sorry, my question is, how certain, I will rephrase my question.
Yep.
How certain are we, so you're talking about the technology.
Right.
How certain are we with the state of climate science at the moment? How certain are we that the intervention would work?
As certain as most things are in science, the volcanic analogs provide pretty clear information. After Mount Pinatubo, the whole planet was cooler by more than 0.5 degrees for a year. Pinatubo was only in the northern hemisphere, so the northern hemisphere was cooler by 1 degree or so. Krakatoa, Tambora, we don't have good scientific records then, but in each of those instances, there was the year without summer and so on. It's quite clear that if we put enough SO2 in the atmosphere, it will cool the planet. But the policymaker is going to come to you and say, well, I want to know what it will do to rainfall in Australia. I don't care about what it does to the whole planet. And those kinds of attribution questions or regional impact questions will be very difficult to unravel. Did I answer the question?
Yes.
Okay. Let me, noting time, move on. Is that the next slide? Yes, it is. So I don't think we will start over the whole planet for a variety of reasons. If we do this at all, and again, it may be a bad idea and we never do it, if we mitigate much more quickly than I'm afraid we will, we certainly will never do this. But if we did this at all, I think the early deployment target would be the poles, not over the tropics to cool the whole planet, because the poles are warming the fastest among the regions of the Earth. The ice melt that happens there threatens sea level rise globally. The permafrost melt that happens there threatens temperature rise globally. September Arctic sea ice has a self-propagating quality to it, so we're losing, the Arctic isn't expected to be ice-free by the middle of the century. Permafrost melt, I've mentioned. Many of the tipping points that are theorized to exist in the climate system are at the poles, not all, but many. The most worrying tipping point in my view, based on when we might hit it and how quickly it would tip and what the damages might be, is the AMOC, the Atlantic Meridional Overturning Circulation, which is why it is that the British Isles and Northwest Europe are as warm as they are. And this is the tipping point that seems most plausibly at risk, maybe in this century. Polar deployments to try to address all of those things, ice melt, permafrost melt, the AMOC, could be done from, say, Anchorage and Stockholm and from the tip of Tierra del Fuego. They can be, again, the stratosphere is high in the tropics and low at the poles. And so if we're deploying in the tropics at 1515, we need these new airplanes that I was showing you earlier that take a decade to design and another decade to build out the fleet. But if we're deploying over Anchorage and Tierra del Fuego, I guess it's the opposite, Anchorage, Tierra del Fuego, we could use existing aircraft. The 777 would do fine at that altitude. And so we could begin much more quickly and much more cheaply. There's the 777. The first thing that is likely to happen in this whole domain is field experiments in either the north or south to try to begin to better understand how to do this. And I'm in fact working right now on a field experiment design that would put out plane load sized plumes in the high north or high south, which is one plane load, no matter which plane we're talking about, is far too little to have any discernible environmental impact anywhere. But it would create a plume that we could then seek to track around the Earth, and then go interrogate that plume in the near field and in the far field to better understand the microphysical evolution of the particles that we put out and where they circulate and how they rise and fall, how long the plume endures as a coherent plume. We wouldn't do if we were serious about this, we wouldn't do this once. We would do dozens of experiments, varying where we put the stuff, how high we put the stuff, what the stuff is. So the experimental regime for this would take a span of years to begin to better understand how to do this. And again, we could do it at either pole. These lines are at 50 north and south. 50 north runs through a territory of a lot of countries, some of whom may not dig this. 50 south is over the Southern Ocean almost the entire way. Although it intersects Chile and Argentina, it comes close to the Falklands, and it comes close to Tassie and New Zealand. Technically, the experiment in the south would be more difficult to access the plume after you've put it out, but politically it might be a lot easier. The purpose of a polar deployment wouldn't be merely to cool the poles preferentially forever. And P.S., it wouldn't cool merely the poles. It's not that well walled off from the rest of the Earth. So even if we vented our material over Anchorage and Tierra del Fuego, most of it goes poleward with the Brewer-Dobson circulation, but a minority of it goes equatorward. And that equatorward minority encounters a lot more sunlight because there's more sun down there. It has much longer atmospheric endurance. And so actually it's a sort of layered phenomenon where we've got a thick layer over the poles, a thin layer over the mid-latitudes, and indirect effects all the way down to the tropics. But the purpose of polar deployment wouldn't merely be to save the poles. It would be to do a lower cost, lower risk experiment to see if all of the problems that we foresee about this technology can be resolved in that more contained environment. If this were deemed to be a positive intervention, you would hope that the deployments would creep equatorward and end up with that global veil that we discussed earlier. So many, many reasons for caution vis-a-vis SRM. There are risks in research. People are worried about the moral hazard or mitigation deterrence effect that this might have, that the world might hear about solar geo and say, well, gee, we don't have to mitigate. That there's no one in geoengineering land who says that. Everybody says you still need to mitigate as quickly as you can, but there's the risk that it slows mitigation. That would be bad. There are fears about a slippery slope. Once we go down this path, it becomes inevitable. There are concerns about deployment. It doesn't address the root cause of climate change. That's totally true. You can't prevent all adverse impacts with this. It wouldn't do a thing for ocean acidification, for instance. It only addresses some symptoms and not all symptoms. As I earlier said, it's morphine, it's not penicillin. The most difficult thing to imagine about this is the governance, how we would create a fair process. There are no institutions that are currently fit for this purpose. There may be divergent preferences regarding climate and therefore climate conflict. But to wrap one's head around this topic, you've got to have the right counterfactual in mind. Where most people want to start is, do I prefer solar geo or mitigation? Well, that's stupid. Mitigation, please do that. That's not the question. Solar geo is not proposed as an alternative to mitigation. The dilemma is, if we're in a too hot world in the future, is it more risky to deploy or not to deploy? That, to me, is a much more nuanced question that we will need more research to answer. So I am all for and dedicated to continuing to try to research this tool so that we better understand it. So I've consumed most of the Q&A time, but I'm not headed anywhere immediately. So further questions?
There's a question online since a long time ago.
I'm sorry.
There's a few people online. Steve, would you like to ask a quick question?
All right. Well, I had two very different questions, actually.
Ask them all the time if you'd be so kind, so I don't have to remember.
Sorry, what was that? I didn't get that.
Fire away, please.
Yes, I had two very different questions. One is, do you have a sense that, I don't know how well you know them, that the economists don't generally address these issues in terms of stock and flows? It's just not in the way of thinking. That's the first question. And the second question is a stupid question, probably, but if, and that's a big if, at some point nuclear fusion becomes economically viable, would that change things or would it not change things? Let's say, at least for this century.
So I'll take them in the opposite order. Nuclear fusion is the get out of jail free card that I'm most optimistic about. That could change everything. And suddenly power would be much cheaper and this fossil fuel energy problem would be much easier to solve. And all of my pessimistic thoughts about the future go away, or at least are much reduced. There are other technologies that could come along that could similarly solve the problem. As I was saying to David earlier, my view is that policy is going to be much weaker in solving this problem than we all hope. What's going to pace the solution to the climate problem is technology. And if technologies are developed more quickly than I would guess that do replace fossil fuels, all of this goes away. Forget about solar geoengineering. We're not doing it. So that would be a great outcome. I just am personally worried about crossing our fingers that technology bails us out, even though we're not sure that it can. Nuclear fusion is 20 years away and has been that for 50 or 60 years, is the old joke, but it never seems to get closer. Your first comment about stock and flow, I guess I'm not understanding the economics connection there. That's a sort of description of the physics of the thing. And the punchline is it's not our emissions that inform the climate, it's the concentration of greenhouse gases in the atmosphere. So I'm not sure I answered the second question.
I think it's a criticism of the economics discipline is what he's making.
I see. Well, but William Nordhaus has won the Nobel Prize in Economics for thinking about not stock and flow exactly, but the cost benefit trade-offs of rapid mitigation. His conclusion in his book 10 years ago is 2.4 C. That's probably the optimal amount of climate change, which is a shocking thought, but he's noting that rapid mitigation has cost.
Okay, thank you.
Yeah, so it's good to have, I think, solutions like even a technology that's something like the last resort. But when you mentioned 2 Indias in terms of reforestation, I began thinking, okay, if we have to go to some level to resolve this problem, reforestation could become attractive at some point, and it solves a lot of other problems as well. Like we have poverty problems, we have water problems, and so on. Why is it hard to get 2 Indias, an amount of area equal to 2 Indias, reforested? For example, we have the Sahara Desert, we have deserts in Australia, we have deserts in the US, places that are not far away from the ocean. We have unlimited amount of ocean water. If we are going to extreme levels to solve problems, why doesn't that become?
So some trees are a great idea. There are clearly places we can plant more trees, and trees soak up carbon, and that's a lovely thing, and it has all sorts of environmental co-benefits. So I'm not against planting trees, but they're the least economically valuable use for land. The least valuable thing we can do is plant trees on it that we can never cut down. This is not lumber. This is permanent forest. People don't want to set aside land for that. We're still doing the opposite thing. You know, Brazil is saying, I don't want to preserve the Amazon. I want to cut it down and make cattle farms. And after all, United States, you did that to your forests, and we have the right to do that too. It's hard to argue against the economic, I mean, the economic solution that often arises is, well, let's pay Brazil to do that. If Brazil is going to set aside its Amazon forest, or we're going to plant a new forest here in Australia somewhere where there's no forest now, if the world is willing to pay Australia to do that, then great. But it's a global service that forest is providing, and maybe the global community ought to pay for it. We're just nowhere near countries being willing to do that. So it's a good solution. I'm afraid it will be a marginal solution. I don't think it will have the capacity to really sort of solve the climate problem. And you can say nothing will solve the climate problem. It's all little wedges that are required. And that's true. As I earlier said, though, the trees are also a fragile store of carbon. We need to get the carbon back down in the Earth's crust, and trees don't do that. But so it's a marginal solution, but it's not an invaluable solution, in my view.
We need to stop for those who need to go. But hopefully you have a few minutes to talk with people now after the seminar, and that'll be great. So maybe we can give Wade a big round of applause. Thank you very much.